In this last part of the section on maximum and minimum values, we're going to be focusing on finding the absolute maximum and absolute minimum values of a function. And in order to do that, we first want to discuss when absolute max and absolute minimum values actually exist. So for that, it really depends on the nature of the function and the domain that the function is defined on. So a little bit of vocabulary to start off with. We're imagining we've got some domain D for our function, and it's sitting in the xy plane. And we're going to think of the domain as all things, potentially on or inside. A point, such as this orange point here, where if I draw any circle around that orange point, no matter how small, it will contain both points inside the domain and points outside the domain. That's called a boundary point. A closed set is a set that contains all its boundary points. And a bounded set is a set that we can fit an entire circle around so that the set is inside that circle. And with those little bits of terminology, those descriptors of properties that sets can have, then that leads us to the extreme value theorem, which says precisely when we can be guaranteed a function has a maximum and minimum value. The statement of the theorem says that if f is continuous and the set that we're looking at it on, the domain, is a closed and bounded set, then f must have an absolute maximum value, and it must have an absolute minimum value. So that's the extreme value theorem. It says that under certain conditions, f is continuous, and the domain that it's defined on is closed and bounded, then it must have maximum and minimum values. So if we look at this next example, we want to find the absolute maximum and minimum values of this function f on this set. The very first question we should ask ourselves is, does it really have absolute maximum and minimum values? If I can know for certain in advance that it has these, then the work I do to try to find them will produce something in the end. If this function did not have an absolute max or min, then I'd be sort of doing some fruitless endeavor. I'd be sort of searching for a unicorn, something that doesn't exist to begin with. So the nice thing about that extreme value theorem above is it tells us definitively, it says, yeah, the maximum and minimum values exist. So feel free to go ahead and do the work to find them, because you will be searching for something that does exist. So why does the extreme value theorem tell us the max and mins exist in this case? Well, this function is a polynomial in x and y, so it's continuous. There's no division by 0 or any of that stuff. So it's a continuous function. And what about the set that it's defined on? Well, the set D is shown there. What is it? X is between 0 and 4. So x lies between 0 and 4, and the y values go between 0 and 3, and they are inclusive. So here's our domain. Maybe I should put it in blue to match with what I did above. This is our domain. That's D. It's a closed set because the boundary consists of these straight lines, and because of the equalities, x is equal to 0, and on the other hand, x is equal to 4. Also, it includes everything in between. So that's a closed set. It's a bounded set because I could stick a circle around it, and it's fully contained in it. There's no parts of this set that go off to infinity, in other words. So it's closed and bounded. Therefore, we know an absolute max and an absolute min exist. So let's go ahead and look for it. How are we going to find the absolute max and absolute min? Well, we're going to do what we normally do. Let's look for critical points, and those are going to be the candidates for extrema. But then I have to be careful, because just searching for critical points is not going to pick up information about what's going on the boundary. So what is our function doing along these 4 boundary curves? So I'll have to analyze those separately. Here's the picture for what we have in mind. this is our function, and we can see that that's the domain we're interested in, x between 0 and 4, y between 0 and 3. So that's what we're looking for. I've actually highlighted in red already the points we're eventually going to find. But if I go ahead and look for the critical points, those are going to be the places where the partial derivatives are 0. And I'm only going to actually find 2 of these points. Why is that? Because when I look for critical points, it's not interested at all in the fact that there's a boundary here. What the critical point calculation is doing, I'll get rid of it, is really just doing a calculation for the whole surface. It's saying, for this whole surface, find the places where the derivative is 0 for the x partial, find the place where the y partial is 0. And that would pick off things like a point over here, which is coming about as sort of a local maximum. It would also pick up the 0, 0 point because that's a saddle point. It would even pick off some more points in other areas. But we're interested in also what's going on the boundary. So the thing to keep in mind is when I do my critical point calculation and find my critical points, I'm doing it, that calculation is essentially doing it for the whole surface, and then you just throw away the points that are outside of the region you're interested in. But I also have to do some further calculation on the boundaries. So if I look at the boundary here, there's a curve corresponding to that boundary. So I'd have to do a calculation that tells me the extrema on that curve. Then I have to look at the next boundary. What are the extrema on this curve? What are the extrema on this curve? And what are the extrema on this curve? So I'd have to do 4 different one-dimensional calculus problems in order to figure out what the absolute max and absolute min values are for this function on this boundary. So let's do that. Let's start with the ingredients for the things we need. We need to know what f sub x is, the x partial derivative, that's 12x minus 4x cubed plus 8xy. We also need to know what f sub y is. That is 4x squared minus 8y minus 3y squared. And so now we're going to use this to find our critical points. How do we get those? Well, we set these equal to 0. F sub x is equal to 0. And then we also have to set f sub y equal to 0. But I'm going to look at f sub x equal to 0 first. And the reason is because I look at f sub x, every term has an x in it, and it also has a 4 in it. So I'm going to factor out a 4x. That leaves me with a 3 minus x squared plus 2y. And that's equal to 0. So that tells me that in order for the x partial to be 0, either x is 0 or x squared is equal to 3 plus 2y. So those are 2 options. So let's consider those 2 cases. Case 1, when x is 0. Since we're looking for a critical point, we also want to solve f sub y equal to 0. So I'm just going to look at the case. The reason f sub x is 0 was because x is 0. So now we're going to look at what makes f sub y 0. Well, f sub y is given by 4x squared minus 8y minus 3y squared is equal to 0. But since x is 0, that's going to be 0. So that tells me then that 8y plus 3y squared is equal to 0. I just realized that both terms were negative, so I just multiply by -1 to both sides of the equation. Or in other words, we get that y times 3y plus 8 is equal to 0. So that tells me then that either y is 0 or y is -8/3. So let's back up. What did we do? We said if the x partial is 0, then that's because either x is 0 or this other expression is true. So we're focusing on the case where x is 0. So in the case when x is 0, then we also need the y partial to be 0. And that y partial is 0 either when y is 0 or when y is equal to -8/3. But if y is equal to negative 8/3, that's not in the domain. So we can throw that one away. And therefore, we have in this particular case, the critical point that comes up is x equals 0, y equals 0. And then what about case 2? Well, case 2 is when x squared is equal to 3 plus 2y. And again, we're looking at when is f sub y equal to 0? F sub y is equal to 0 when, well, f sub y is 4 times x squared, but now I can use x squared is 3 plus 2y. So it's 4 times 3 plus 2y minus 8y minus 3y squared is equal to 0. So that's just an equation in y alone. That becomes 12 plus 8y minus 8y, those cancel off, minus 3y squared is equal to 0. Or in other words, 3y squared is equal to 12, or y squared is equal to 4, or y is equal to either 2 or negative 2. 2 or negative 2. But again, we can get rid of that negative 2 because it's not in the domain. Y has got to be a value between 0 and 3. So therefore, xy is equal to, we just solved it, we got y is equal to 2. What is our x value equal to? Well, now we go back up to our relationship. X squared is equal to 3 plus 2y. So when y is equal to 2, x squared is 7. So x has to be plus or minus square root of 7. But in order to be in the domain, x has to be between 0 and 4. So that means it has to be root 7. And so there are our two critical points. There's our two critical points. So if we're looking at our picture up above, in terms of our domain, we've got 0, 0. And we got another critical point that's at y equals 2 and square root of 7. So what's the square root of 7? A little bit below the square root of 9, a little bit below 3. So it's somewhere around here. That's our other critical point. So we got those two critical points. If we go back to our visual, then I just drag it around, sort of look at our perspective that we've got in our diagram. We picked off the 0, 0 point, and then we've picked off this point that's, sort of, it's that red point that's in the upper right-hand corner, just sitting there on the blue surface. So you can see it sort of peeking out there at the top now. That's the other point. But we still have a bunch of other points that we have to figure out how to get and where they're coming from. So let's move on to those ones now. Okay, so we got our critical points. Now comes the boundary analysis. Because our function is restricted to this domain D, there could be maximum and minimum values that occur on the boundary. And so we have to look at those separately. So here's our boundary. And we do this by reducing to a 1D calc problem. Well, a bunch of 1D calc problems. And it goes as follows. So we'll redraw our domain up to 3 over to 4. So there's our domain that we're interested in. And so we'll focus on our domain by looking at the boundary curves. So there's one curve. Let's call that curve L1. There's another one here, which is L2. There's another one here, which is L3. And another one here, which is L4. So for these boundary curves, we're going to do the following. For L1, that is when y is equal to 0 and x is trapped between 0 and 4. And I'm interested in knowing, on this curve L1, does our function have a maximum or minimum value? And if so, let's figure out what it is, because I'm going to compare it to the maximum and minimum values of the function that appears on the other boundary curves, and also compare it to the critical points that we've got. So what is it? Well, we're going to write down what our function is on this particular curve. It's fx0, fx0. So I'm looking here up at the top at fx, y is equal to 0, so that's going to be 6x squared minus x to the fourth. 6x squared minus x to the fourth. I want to know what are the maximum and minimum values of this. This is a 1D calculus problem now. What are the maximum values of this function of a single variable? We can find its critical points, differentiate, set to 0, find the critical points, and then figure out which one's biggest and which one's smallest, compare it with the value of the function at the endpoints, the value of the function when x is 0, the value of the function when x is 4. So we can do all this, solve this 1D calculus optimization problem. So if I do it, and I get the critical numbers here, what I get is that x is equal to, and then I'll just hang on to the y value as well. So x, y are equal to 0, 0, or x could be root 3, and then the y value is 0. The y value is always 0 because that's the curve we're on. We're on the y equals 0 curve. So we can consider these as like the boundary critical points. They're the points along this boundary curve L1 where there's a potential for having a max or a minimum value. And they were coming from solving this 1D calc optimization problem. And I'm going to make a note that we also have endpoints. The endpoints are x equals 0 and x equals 4. In fact, I'm going to write the endpoints down as a pair because I'm really interested in them as a pair. So the endpoints are 0, 0, and the endpoints are when x is 4 and y is 0. Okay, we already got one of the endpoints as an actual critical point, so we could probably even remove that as the endpoint because there's not much information there. So that's what we got. We've got two critical points, and we've got this endpoint, the x equals 4 endpoint. Those are the possibilities for maximum and minimum values of our function f along that boundary curve. Let's do the next boundary curve, L2. So for L2, that's when x is equal to 4 and y is between 0 and 3. So our function is going to be 4y. And if we write down what 4y is, well, it's 6 times 4 squared minus 4 to the power of 4 plus 4 to the power of 3y minus 4y squared minus y cubed. So plugging in x equals 4 into our expression for our function. Now we've got a function of a single variable. And again, I'm just going to pop over because sometimes it does, one can get sort of lost in what it is we're actually doing here. So I'm going to pop over to our visual. What we're doing is, again, we're looking at this right-hand vertical boundary line. So I'm going to look at our perspective from, or look at our surface from that perspective. So I'm looking at our surface. In particular, how is it behaving along that boundary line? And we can see that it starts down at the bottom left at that red point, and then it goes up to the red point that's at the right-hand side. So I've got this part of my surface on this boundary curve is behaving like this increasing function. And so I've got a minimum at the left-hand endpoint and a maximum at the right-hand endpoint. The way we would get this from our calculations would be we would look for the critical numbers here, take its derivative, set it to 0, figure out what the y values are, and it turns out we get none. There are no critical numbers. So we could do that calculation and get none. That's a calculus 1 problem, so I'm sparing the details here. But you can do this yourself. Differentiate, set to 0, see that there's no solutions. So that means that along this curve L2, our surface has or our function f has maximum or minimum values that would occur at the endpoints. And so we'd have to keep the endpoints in mind. The endpoints are x equals 4, y equals 0, x equals 4, y equals 3. Now we'll do the same thing for the next curve, L3. For that curve, we've got x can range between 0 and 4, y has a value of 3, so our function is given by f of x3. That's now a function of a single variable. We plug that in and we get 6x squared minus x to the 4th plus 12x squared minus 4 times 9 minus 27. You can do a little bit of simplification on that. Look for the critical numbers for that function of a single variable. And we get that the critical numbers are going to be 0, 3 and 3, 3. And are there endpoints? Well, if I look at my picture above, 0, 3, x equals 0, y equals 3 is that point. 3, 3 is a point around here. And then we'd still also have to include the endpoint. I still need to include that point there. So what is our endpoint? Our endpoint would be x equals 4, y equals 3. So we'd include that point as well. And maybe I'll fill in the special points that we found on the boundary. You know, for the L2 boundary curve, it was just the endpoints, 4, 0 and 4, 3. So I don't need to include that upper right-hand endpoint twice. For the lower one, it was 0, 0, which also is an endpoint. It was square root of 3 and 0. So that's somewhere around there, and 0, and then the endpoint 4, 0. So we're just walking our way around the boundary, solving 1D calc problems as we go. And then we've got L4. What's L4? L4, the function on L4, well, that's where x is equal to 0 and y can range between the values of 0 and 3. So our function is going to be 0, y, so it's a function of y alone. And that's negative 4y squared minus y cubed, which is negative y squared 4 plus y. Then we'd like to find the critical numbers for this one. So we take its derivative, set it to 0, find our critical numbers. We get 0, 0. We'd also get the value 0, negative 8 thirds. But that one we would throw away because that y value is not in the domain. And then we'd also have our endpoints. And our endpoints are, we've already got 0, 0, which came up as a critical point. And our other endpoint would be 0 and y equals 3. And so what we have now is we've got a number of points that are also candidates for the absolute max and absolute min of our function. Those are these red points that I've indicated in that diagram on the left. And we have, I'll add the specific values here for the ones that aren't clear to read off. So there's this one, which is root 3, 0. And then we also have this one in the top L3 line segment, which is 3, 3. And then we also, it wasn't part of the boundary results, but we also had that other point. We'll scroll up. We also had that orange point above. That was the critical number. That was the root 7 and 2 point. So that was the square root of 7 and 2. So we got a bunch of points now that we have to check. Okay. So what is our absolute max and min values? Well, what we do is we compute f at all the critical points. So those are because the surface was doing something, either a maximum or a min, local max or a local min. And so we're going to check those, the critical points, to see if any of those local max min are actually absolute max and mins. But we're also going to check the function values at the boundary critical points, the critical points that we got for each of the 1D calc problems on the boundary. So we're going to compute f at all the critical points and what we call boundary critical points. Boundary critical points. And so what are those? Those are f at 0, 0, f at root 3, 0, f at root 7, 2, f at 3, 3, f at 0, 3, f at 4, 3, and f at 4, 0. So those are all the points that we had. So again, let's make sure the count is right. I'm counting 1, 2, 3, 4, 5, 6, 7 points that we got to evaluate at. I have 6 coming up from the boundary from this diagram, plus the 7th one that's inside the domain, that root 7, 2 point. So those are our 7 points, and now we're just evaluating the function at these 7 points. So this one's 0, this one's 9, this one's 25, this one's 18, this one's negative 63, this one's negative 31, and this last one is negative 160. And I just compare. Which one's biggest, which one's smallest? So the biggest number is that one there. So that's our absolute max. And it occurred at root 7, 2. So it was the one that occurred from the critical point of our multivariable function. It's occurring inside the domain. What's our smallest value? Our smallest value is this one here, negative 160. And that's our absolute min. And it's occurring on the boundary. So we found our absolute max and we found our absolute min. Let's go to our visual to see if this agrees with what we see there. So if I look around, well, I can see the absolute min. It's this point way down here. That's coming from x equals 4, y equals 0, and that's that negative 160. And we can also see it from the marking down here that I had when I set the axes up. I had to set it down to negative 160 in order for it to fit in there. So that's our absolute min. Our absolute max, the highest point on the surface, is this point right in the middle of the surface there, or near the middle of the surface. And that's coming from that point, root 7, 2, and it had a value of 25. And if we look at the scale on our z-axis, yep, we see it's about at a height of 25. Okay, so that's it for this example. The main takeaway from this example is that in order to find the maximum and minimum value of a function on a closed, bounded domain, we're going to have to do a critical point analysis inside the domain and then a boundary point analysis around the boundary curves. And those are reducing the problem to calculus 1 problems. Depending on how many segments you use for your boundary curve, you have to solve that many calculus 1 problems. We used 4 segments because it was a rectangle, so we used a line segment for each side, and we solved 4 1D calculus problems, and then brought everything together, all our critical points and our boundary critical points, compared the values, which one was biggest, which one was smallest. That gives us our absolute max and our absolute min. Alright, that's it for this section. Thanks very much for watching, and we'll see you again next time.